right, let's take a look at today's lesson. We're going to be working with slope fields today. And when I was in college, we didn't have slope fields. Well, I'm sure they probably were in development. Maybe somebody had come up with them already. But we really didn't have computers that would do that for us. So it's kind of it's a topic that's come with technology, the slope fields have. So what they are, let's talk about what they are. Each one of these little lines represents the slope at that location. So let's go back to integrals. We talked about that it's impossible to solve every single integral. There are some integrals you cannot do by hand. And so we have approximation techniques to handle that. This is really a visual approximation technique. What this does is it takes the differential equation that you have, and since we have the differential equation, we can plug points into it, right? You know, when x is 0, y is 0, and so forth. And we can find out what the slope is at the location. And so that's what is happening here. Each of these little locations is a small little slope, a picture of what the slope looks like there, so that we can get a general idea of what the shape of the solution would look like. So in this particular case, this is a slope field for the differential equation y prime equals y minus x squared. And down below, what they've done in blue is they have drawn possible solutions, or the solutions in each of these little areas. So this is what the position function might look like, okay, in this piece. And we can't really tell what they're using, you know, what their scale is, but in this location, the position function would look somewhat like that. And we have a few different examples. Here's another differential equation with its slope field and some possible solutions drawn in. Notice this straight line right here, this one. That one is called an equilibrium solution. If you recall back a couple of days ago, we were doing vocabulary words and we talked about equilibrium solutions are constant solutions that visually represents a horizontal line. So this would be classified as an equilibrium solution in this particular one. And then a third example of what a slope field would look like. So there are, for several years, I have seen slope fields on free response on the AP test. It's usually a part of a bigger question. They have you draw slope fields. You also have to know how to read slope fields. And so we're going to do both today. We're going to learn how to read them, and we're also going to learn how to draw them. So that's our objective for today. First, let's start with reading them. Let's just learn how to read them. A direction field, it's another name for a slope field. Those words are interchangeable. So we have a direction field for the differential equation. We actually have the equation here, the differential equation, and this is the slope field that's generated from it. What they're asking us to do is sketch the graphs of the solutions that satisfy the given initial conditions. So we're going for something like this. You know, we're going to be drawing solutions on our slope field. Now, it seems like a very simple task, but some students have a really hard time with drawing solutions. So let's talk about it as we do it. What we're going to do, our first step, is to go to the location where they say the solution goes through. This initial condition is when x is 0, y is 1. So we want to go there when x is 0, y is 1. And we want to just go ahead and put a point. Now, the way we determine what to do is we just look to our right and left. Let's start with the right. And we want to follow, think of it as like a river. Okay, you want to follow with the flow of the river. You don't want to like jump through the waves and cross into, you know, just draw lines. You want to follow how it goes. And if we'll look, following it out this way, and then it kind of tapers off. I've been asked, do I need to draw the line on the little slope fields or between them? And it doesn't matter. It's not a very, very precise thing that we're doing. We're just going with the general area, the general shape of what the solution would look like. So moving to our left, it would flow, we're just going where it's pointing, you know, it points us right out there. Okay, so that would be the solution for this one. All right, let's do another one. Okay, let's do this one. When x is 0, y is pi. So 0, let's see, there's 3, so pi would be a little bit above it. And it looks like, see, as we go right and left, those are all horizontal lines. So it appears that this is an equilibrium solution. All right, and let's look at our last one. When x is 0, y is 5. So let's go up here. And again, we are trying to look and see, draw our solution so that it kind of flows with the little slope lines. So as I'm going right, looks like it's coming down like this. As I'm going left, again, it looks like it's coming down, going this way. And so that is an example of drawing the solutions. Okay, how are we with that? Is everybody okay? All right. This part B asked us to find all equilibrium solutions. We found one when we were drawing our slope field. We see this is, y equals pi. So we need to look for patterns, or maybe look in the slope field and see if we see another one. It might be kind of hard for you to see out there, but the x-axis has like little slope lines on it, little horizontal slope lines. So this is another equilibrium solution at y equals 0. So we look for clues. So we looked for a clue in the slope field. Now let's look for a clue in the actual differential equation. It's got a trig function in there. We know that trig functions are periodic. So what could we get from that? What would that imply? Is it only just these two equilibrium solutions, or perhaps are there more? There are more, right? There are more. Now, if you're really unsure and you want to test it, if you're, don't believe it, you can certainly substitute values in here to determine. It looks to me like our equilibrium solution is pi n. So every pi, there's going to be one up here, and every pi spaces, there's another equilibrium solution. Okay, that would match. Okay, is that okay? All right, so that's some examples of working with a slope field. Now on the next page, we're going to draw some slope fields. All right, so let's go do that. Just the equation of the line, y equals pi n, so pi or 0 or pi, 2 pi or 3 pi or... that would be a specific one. That would be a specific solution. All right, so again, on the AP test, the ones that I've seen have dotted grids like this. And when they give you a slope field like that, they expect you to put slope lines on every single dot. Okay? It's not a pick and choose thing like, oh, I like this point better than that one, or this one's easier than that one. It's all of them. They want you to draw a field. Now, I'm not going to give you like a 100 by 100 grid and you're going to have to draw 100 little lines. I'm not going to do that, and they don't do that either. It's just a sampling. And so it will be to our benefit if we could find a pattern. That would save us some work. So let's go ahead and let's start this one. What I do is I draw a T-chart. And I just pick sample points, and I like starting with 0, 0. I just kind of like that, the origin. So what I do is I choose a location, and then I sub those values into this equation to come up with the slope. That's all I do. So I sub in a 0, 0, and I get a -1. So I would go to the location, the origin 0, 0, and I'm going to draw a slope of a -1. Okay, Sure. On this one, so again, this is a start in recognizing patterns. On this particular one, does it matter what the y value is? It doesn't, right? Because I don't have a y in here. And these types actually prove to be a little more simple than the others, because what if x was 0 and y was 1? I'm still going to have a slope of -1, right? So that's a pattern that we would look for. So let's just follow that pattern. If x was 0 and y was -1 or -1, and we were still going to get this slope. So I'm able to use that information, that knowledge, and fill in that whole column. Okay. All right. So let's take a look. Let's do 1, 0. And in fact, this column doesn't even matter. And another thing is, I don't need to see this. This isn't required for me. If you don't want to do a t-chart, that's fine. You can do them all in your head and just write them on. It's okay. What I am going to require is that every dot have a slope field on it, a slope line on it. All right, you can do them all in your head if you like. I'm just showing you, giving you a structure if you want to use the structure to do it that way. All right, so when x is 1, my slope is 0. So that would be a 0 slope. And so we just talked about the pattern, right? It doesn't matter what y is, it's still going to be a 0 slope all along this location. Okay. So let's check it out when x is 2. 2 minus 1 is 1. So when x is 2, we have a slope of 1. And following our previous logic, we're able to fill that whole column. When x is 3, our slope is 2. Now what we're looking for here, and to draw a slope of 2 by hand without like a normal grid, that is not very easy to do. What we're looking for is a pattern. So we need that our slope of 2 to be steeper than the slope of 1. We just need it to look steeper. And so we would go over here and just try to draw just a little bit steeper lines than the lines that have a slope of 1. Okay, we're just looking for that pattern. So if x was -1, let's see, -1 minus 1 is -2. So again, I'm looking for, just to make it a little bit steeper than the one beside it. Okay, hopefully you see a pattern as we keep going left. So if this slope was -2, this one's going to be -3 and then -4, right? So we're going to get a little bit steeper and a little bit steeper. So let's just do that. And you know, they could be quite exaggerated because it's really hard to show that small of an increment. So you can exaggerate them just so that you can follow the pattern that it is getting steeper. Does that make sense? Okay. Our very first slope field. Not too bad, right? Yay! Not too bad. Some students love this and some students cannot stand this because it takes a few minutes. All right, so let's do this one. Okay, I'm going to start with 0, 0 again, just because that's where I like to start. You can start wherever you like. So, okay, so we should notice this now. This differential equation doesn't have an x value. So that's going to be beneficial, right? So it only has a y value here. So when y is 0, my slope is 0. Okay, so y is 0, my slope is 0. And what can I interpret from that? Yeah, all of them, right? All the way across. There's just going to be 0. So that's nice to be able to follow that pattern. Now let's look to see what happens when y is 1. When y is 1, I'm at a half. So we know the 1 slope is pretty straightforward, right? It's 45 degrees. So we just need to make sure for a slope of a half, it needs to be a little bit flatter than a 1 would be. And so when y is 1, up here, we're going to have a slope of a half. So it should be a little bit flatter than a slope of 1. And when y is 2, my slope is 1. So here would be a normal 1 slope. Oh, got a little carried away over there. Helps to have an eraser with these. Alright, so let's see what happens when y is -1. So then I'm at -1/2, and again, just needs to be a little flatter than a -1 would be. -1 would look like this, and so -1/2 will just bring down a little bit flatter. And then the last one is when y is -2. What are we at? -1. So we would look like that. Okay. All right, our last one. We have an x and a y in here, so it'll be a little bit more challenging than the ones that we just did. Okay, I'm going to start at 0, 0, again, just because that's where I like to start. So at 0, 0, I have a slope of 0. While we're there, let me just point out, I don't have one here in the examples, but what would make my slope undefined? Could I get, so let's say my, it was this. Let's say my differential equation was this. 0, 0 would be undefined, right? If y is 0, it would be undefined. How do we make an undefined slope? How do we show that? Yes, a vertical line. I've seen actually two techniques. I've seen vertical lines and I've seen blanks, just not drawing anything. So either of those is fine. You could choose to do either of those, either a vertical line or to leave it blank. Yeah, vertical line works. Vertical line works. All right. So here, our 0, 0, we're at 0. Can we think of any other place we would be at 0? Yeah, 1, 1, right? At 1, 1, we're going to be at 0. It's going to be like a diagonal. So at 1, 1, we're at 0. At 2, 2, we'd be at 0, right? -1, -1, at 0, and so forth. All right, so we have a pattern going on there. Not the same type of pattern we had above, but still pretty good. Let's see, what if x was 1 and y was 0? We would have a slope of 1. Okay, so 1, 0, we have a slope of 1. Where else might that be true? Do you think the diagonal pattern is still going to work for us? It will, right? Because here we'd be at 2, 1. 2 minus 1 is 1. So we have a different kind of pattern, but still a good one. All right, so now let's just fill in. So if we're at 2, x is at 2, 0, then our slope is 2. So a little bit steeper. Oops, that's a bit too much. Okay, a little bit steeper. And as we go out, can you see what's going to happen? It's going to be more and more steep, right, as we go up by the diagonal. So I just need to draw this, a little bit steeper than the one before, kind of exaggerated. What happens if x is -1? So let's see, -1 minus 0 is -1. Okay, so if x is -1, we are at -1. And let's see if that same pattern continues. If x is -2, our slope is -2, so it's more steep, right? It's the same kind of pattern going left that was going right. As I go left, it's going to be just a little bit more steep. Kind of exaggerated. All right, so how is our slope fields, drawing slope fields? We're okay with that? Not too bad, right? Okay.